Hey there, welcome to my first live stream. I'm James M. Powell, and today we're going to be discussing why the Hubble tension is not a crisis in cosmology. Okay, we'll be looking at how the James Webb Space Telescope data actually supports a finite universe with a three-torus topology, and how that resolves the Hubble tension when you correct some of the fundamental assumptions at the root, and then they naturally lead to a resolution at the top. So, let's get into it. I'll be reading from some notes. There's a lot to talk about, so I've got some notes here. And, as we go through the live stream, feel free to leave your comments and your questions, your thoughts below, so, we can engage in conversation. We can see if this actually resolves the Hubble tension. I want to see what you think about this. Okay, so today, we're going to be discussing one of the biggest puzzles in cosmology. Okay, but we're going to break it down into plain English so we can all understand it. And you know, I'm going to break this talk down into sections like 1, 2, 3. We're going to go through each part together, and we're going to see where it leads us. Okay, so it's going to be very exciting. I don't think we need to struggle with the Hubble tension anymore. I was just watching a YouTube video of quite a famous, popular, cosmologist, astrophysicist, and I see them all the time, right? Saying how much of a mystery or a puzzle this Hubble tension is. I don't think we need to. We don't need to struggle with it anymore. So, let's see where this goes. Okay, so, section 1. This is the persistent discrepancy in cosmological measurements. Okay, so for more than 10 years, scientists have seen an uncomfortable mismatch. Okay, there's two totally different ways of measuring the Hubble constant. Okay, so simply the number that tells us how fast the universe is expanding, and they keep giving different answers. Okay, there's a discrepancy, both of which are, according to the instruments that we're using to measure it, are correct, but they seem to be different. So, this is the big kind of puzzle, right? So, one method looks at the cosmic microwave background, or CMB. Some call it CMBR. A lot of people want to drop the radiation part. But that's the faint leftover glow from the Big Bang, okay, which is like a baby picture of the whole universe when it was very young. And so when combined with our standard model of the cosmos, okay, called the ΛCDM model, okay, which is where lambda stands for the dark energy speeding up the expansion, and CMD stands for cold dark matter, okay, the invisible glue holding galaxies together, it gives about 67 kilometers per second per megaparsec. Okay, so the other method uses nearby stars and exploding stars and gives 73 to 74 kilometers per second per megaparsec. Okay, that's an 8 to 10% difference in the famous Hubble tension. Right now, the strengthened Hubble tension with the James Webb Space Telescope data. And this newer data, it's made it even stronger instead of fixing it. We were hoping that it would resolve, and that this new information that we get from the James Webb Space Telescope would just paint a clearer picture, but it's actually made it a lot worse. Okay, so there's actually information in there. There's clues that point to actually what how to resolve it, essentially, right? So the limitations of the conventional infinite universe framework. Okay, we're going to look at the limitations of assuming that the universe is infinite. Okay, so most researchers have assumed the universe is infinite, that it goes on forever in every direction and looks roughly the same everywhere. Okay, they've thought that the tension means that we need brand new physics, like changing dark energy or extra invisible particles. Okay, but even the incredible new images from the James Webb Space Telescope, our most powerful space telescope yet, haven't made the mismatch disappear. In fact, it's made it even stronger. Okay, so maybe the real issue isn't missing physics. Okay, maybe we've been wrong to assume that the universe is infinite. Okay, so I remember looking at this and I was thinking, what if we're not measuring the same thing? What if these are not two measurements of the same thing, but they're each a measurement of a unique aspect, two different things related to the expansion? Again, I was thinking, what about the difference between frequency versus wavelength, and that turned into global averages versus a more local measurement? Okay, so let's get into this. So the core claim is a finite three-torus universe resolves the strengthened Hubble tension. Okay, so the straightforward solution is that the universe is finite and shaped like a three-torus topology, as a three-torus topology. Okay, so finite just means that it has a limited overall size. And a three-torus is like a three-dimensional donut or a video game world that wraps around and you fly off one side, you reappear on the opposite side. And topology is the math of how space is connected and shaped. Okay, so in this geometry, the CMB, the cosmic microwave background, the light, can't have waves longer than the size of the whole universe. Okay, so if the universe is infinite in size, then we would expect to see an infinite range of wavelengths in the CMB, the cosmic microwave background. But if the universe is finite in size, then we would see a specific wavelength cutoff, okay, because the wavelengths cannot be bigger than the size of the universe. Okay, and that's exactly what we see in the data, okay, in the James Webb Space Telescope and the ESA satellite data as well. And that's a very clear indicator that the universe actually is finite in size. And based on that information, also we can determine its topology. Okay, so when scientists analyze the CMB while still assuming infinite space, they get a lower expansion rate by mistake. Okay, because we're talking about global averages, okay, across the whole system. But local measurements are on a much smaller scale, okay, and they don't feel that wraparound effect at all, okay? So they give the true higher Hubble constant, and there's no new exotic physics required at all for that, okay? So you have this global average, and then you have the local more direct measurement as well. Okay, this idea is laid out clearly in the first paper that I want to highlight, called Resolving the Hubble Tension Through a Finite Three-Torus Topology, Why Global and Local Measurements Might Naturally Disagree. That's hosted on Zenodo. That's the open access science paper repository hosted by CERN. The links are in the description. Okay, so zenodo.org/record/1834798 again, the links are in the description. I published that on January 23rd, this year, 2026. Okay, so the second section is we're going to be examining the rigorous examination of the evidence. Okay, so the human contexts of data conflict. Okay, the newest James Webb Space Telescope observations of special pulsing stars, and which they brighten and dim like reliable clocks, right, are used as distance rulers. Okay, we use them to measure distances, okay, in space, like type 1a supernova, white dwarf stars that explode with almost exactly the same brightness every single time. Okay, so they're very reliable, and it's another great distance ruler. Okay, so they have locked in that higher local value at around 73 to 74 kilometers per second per megaparsec. Okay, so the CMB data from the Planck satellite still points to the lower value of about 67 if you use the usual infinite universe math. Okay, that's if you use the infinite universe math. Okay, but many scientists feel stuck. So what if this disagreement is not a flaw? Okay, what if it's exactly what you'd expect in a finite donut-shaped universe? Okay, so let's examine the evidence for and against this idea. So in an infinite, perfectly uniform universe, the two methods should agree better as our telescopes improve. Instead, the James Webb Space Telescope has made the gap more obvious. Okay, so this conventional explanation is struggling. We keep seeing the same 8 to 10% difference no matter which distance tools we use. Okay, if the universe were truly infinite and smooth, that offset should shrink with better data, but it hasn't. Okay, this should serve as a huge clue. Okay, so the 3-torus idea fits the data cleanly and keeps things simple. Okay, the biggest ripples in the CMB can't be bigger than the universe itself. So the CMB looks slightly squashed when analyzed under the infinite assumption. Okay, that makes the calculated expansion rate come out too low. Local measurements stay accurate because they're tiny compared to the torus size, the global size. Okay, they're tiny. So the more direct measurements are the accurate measurements, and then you have the global averages, which are lowered based on infinite universe math. Okay, this follow-up is explored in the second paper, my follow-up paper to my original preprint, and I've called it Resolving the Strengthened Hubble Tension, James Webb Space Telescope's Local Measurements in a Finite 3-Torus Universe, follow-up note. So this is also on Zenodo, and you can find that under zenodo.org records 18496497. Okay, published February 5, 2026. Okay, I've linked that below or in the description of this video as well, so you can just click on that and take a look yourself and let me know what you think. So, practical application for other researchers, like if you're working on any science puzzle, try instead of adding more complicated pieces, ask whether a finite or finite size or wraparound shape could explain both conflicting results at once. It might completely change how you see your data. We're looking for simplicity, not just adding extra stuff all the time to see if we can fix something when, actually the data's hinting at something else, right? So section 3, a parsimonious resolution to the Hubble tension. Okay, the insight that realigns the data, right? When we apply the finite 3-torus geometry or topology, the numbers line up naturally. Okay, this is what I'm saying. When you correct some of the fundamental assumptions, then it leads to a natural resolution. Okay, so the problem would just go away because we have corrected some of our fundamental assumptions. Okay, so the CMB gives a biased low value because of the universe's size limit. Okay, James Webb Space Telescope's local measurements give the real expansion rate. What looked like a crisis becomes a beautiful clue. Okay, the universe is finite, connected like a 3D donut, and bigger than the patch we can see, but not infinitely huge. Actually, based on the data, we can see that it's about 3 to 4 times that of the observable universe. I reckon 3.14, but that's a guess. But this is information that's coming out of Lyon University in France and Ulm University in Germany, as led by an astrophysicist called Thomas Buchert. And he hasn't had any input into what I'm saying today, but it's based on that the information that he's put out there, based on from the NASA and ESA satellites, from the CMB and all that. So he's already published a bunch of papers on that. Very grateful for his work. And so I've taken that research and I thought, what if we plug that into what we assume is an infinite universe, correct some of those assumptions at the root and see what happens at the top, right? And seems to lead to a natural resolution. Okay, so key conclusions from the analysis. Okay, the Hubble tension is not a sign that we need wild new physics. Okay, it's exactly what a finite 3-torus universe predicts. Okay, we're also talking about back reactions and stuff like that as well. Okay, it's all built in, not like a hard boundary, but it's coming up against a boundary and it's coming back kind of like a standing wave. So, there's interactions and stuff going on as well, right? So James Webb Space Telescope, higher local value, 73 to 74 kilometers per second per megaparsec is the correct one. And the lower CMB value is the expected topology bias, right? We don't need to change the lambda CDM model at all. Okay, we just need to drop the old habit of assuming space goes on forever. Okay, that single change makes everything consistent and much simpler. Okay, so here's a few things we can do, right? 3 steps. Okay, one is stop defaulting to the infinite. Okay, global measurements like the CMB and local ones can differ for natural geometric reasons without breaking the standard model. Okay, 2, look for scale-dependent clues. right? Treat mismatches as possible hints of boundaries or wraparounds. Okay, and 3, ask the topology question. Okay, so for any new observation, ask the question, what finite shape would make both data sets agree? Okay, and test it. Okay, so, just to recap, these 2 Zenodo papers gives a straightforward math-based picture that brings the James Webb Space Telescope and CMB results into harmony while keeping the core of our standard model intact. Okay, no speculative new physics needed, just a smarter assumption about the universe's overall shape or topology. Okay, so before the end of this week, open both papers. I've linked them in the description. Take a look, read them in detail. Okay, look for 3 torus wavelength cutoff, a scale-dependent bias, and note everything that you find. Okay, do we really have to struggle with the Hubble tension anymore? I don't think so. Okay, I truly think this has been solved. I truly think that this solves the so-called crisis, the Hubble tension. Let me know in the comments what you think. Once you've read the papers, you've taken time to look at them, let me know what you think. I'd like to see, how this stands up as well. So, just let me know. So yeah, what stood out to you? Is it the fresh interpretation of the tension, the topological donut-shaped universe explanation, or what this means for future observations? I think it's a very exciting time, that we live in. This is, everything's open to us. We can actually, we can solve everything. That's my honest belief, my conviction. We can find the answer to every question. So I think it's a very exciting time. So yeah, let me know, read the papers and let me know what you think. And yeah, let's see where this goes. Take care.